good day. So we are on the last part of the solution of a first order differential equation, and that is the methods by substitution. So there are actually two parts of the methods by substitution. The first part is about homogeneous equation, and the second part is about linear in two variables. And at the end of this presentation, so it is our task to identify if a given first order differential equation is homogeneous or not. And the second one is to identify if a first order differential equation is linear in two variables or not. So these two objectives could be easily attained. So since a linear equation in two variables can be easily distinguished on a given differential equation, and together with the first order differential equation in or homogeneous equation could be easily determined as well. So once we were able to get the degree of the homogeneity of the given equation. And lastly, of course, is we want to find the general or the particular solution of the first order differential equation by using either the homogeneous equation or the linear in two variables. So to start with, so the first part of the video presentation is about the homogeneous equation. And then I'll have another video for the linear in two variables. So since that involves two different cases. So in homogeneous equation, so the function of f of x and y is said to be homogeneous of degree k in x and y if and only if the function is multiplied by a lambda both for x and y, and then it would yield a common factor of lambda raised to k, multiply it with the function of f of x and y, wherein k here so would correspond to the degree of the homogeneity of the given differential equation. So that is what we will be doing for homogeneous equation. That is on how to detect so whether a given equation is homogeneous or not. So we could do it mathematically, so by looking at the degree of the homogeneity, or just by simply observing or looking at the given differential equation, so you could easily detect so whether that is homogeneous equation or not. So these are the steps that we will be following or before we'll proceed there. So there are examples here so on how to determine the homogeneity of the given equation. So for example, if I would have 4x squared minus 3xy plus y squared. So in this case, this would be our f of x and y. So that is 4x squared minus 3xy plus y squared. And in order to detect the homogeneity of the given differential equation, so we're going to substitute lambda x in place of x and lambda y in place of y. And as you can see here, so we are substituting lambda x in terms of x and lambda y in terms of y. And from there, so simplifying the equation, so that would result to 4 lambda squared x squared, and then minus 3 lambda squared xy plus lambda squared y squared. And from here, so we could factor out lambda squared. So the lambda squared would be multiplied with 4x squared minus 3xy plus y squared. So that gives us, this is actually the same as the lambda squared, then multiply it with our original function, so which is this one. So therefore, the degree of homogeneity of this given differential equation then would be 2. Okay, so therefore, this given equation can be resolved using the methods for homogeneous equation. So to better understand on how to get the degree of homogeneity, so let's have another example. So in this one, it involves a radical sign. So let's check that our f of xy here is equal to the square root of x minus 1. And again, so to check the homogeneity of this given differential equation, so we're going to change x into lambda x while y into lambda y. So giving us the square root of lambda x minus lambda y. And as you can see there, so we could factor out lambda. So giving us the square root of lambda, multiplied it with x minus y. And since that would be a product, so we can get the square root, okay, the root of the lambda. And that would give us the lambda raised to 1/2. And then that would be multiplied it with the square root of x minus 1. And again, the lambda raised to 1/2, this is the same as our f of xy. So as you can see again here, that our f of xy is actually the square root of x minus 1. So giving us here as a homogeneous, and the degree of homogeneity is 1/2. Okay. And lastly, for example, we have this another one, so the 2y cubed, and then the exponential. Okay, this is exponential y over x minus x to the fourth all over x plus 3y. So f of xy then would be equal to 2y cubed. Okay, change y into lambda y, and then the exponential function lambda y all over lambda x, then minus lambda x raised to the fourth over lambda x plus 3 lambda y. And from there, so we could distribute or could expand this one. So this would give us 2 lambda cube x cubed, and the exponential, so the lambda would just cancel out. So giving us y all over x, and then minus lambda raised to the fourth, x to the fourth all over, in this case on the denominator we could factor out lambda. And thus simplifying it further, so giving us 2 lambda cube x cubed, then the exponential function y all over x minus, we could cancel out x there, so leaving us a lambda cube. And as you can see here, so we could factor out lambda cube and lambda cube there. So giving us lambda cube, multiplied it with 2x cubed exponential function y all over x minus x raised to the fourth all over x plus 3y. And again, the whole of this is equivalent to our original f of xy function as stated above. And then from here, so we could see that this is a homogeneous equation, and the degree of homogeneity would be 3. Okay, so that is on how to check the degree of homogeneity of the given differential equation. So take note that the degree of the homogeneity, so once we proceed with our steps in finding the solution of a differential equation for homogeneous equation, the degree of homogeneity will always cancel out. So let's proceed with the methods to follow in solving a homogeneous equation. So once we have detected that it is a homogeneous equation, actually we can easily look at that one without even solving it. So we're just going to take a look the term by term degree. And if all the terms would have the same degree, therefore that is a homogeneous equation. So let's have the different methods. So we have 3 methods on how to find the solution of a homogeneous equation. The first one is homogeneity. So we have to take a look whether the given equation is homogeneous or not. So we could either use the methods using lambda, so changing x into lambda x and changing y into lambda y. But if you just simply want to take a look at the given equation term by term, that would be okay as well. Okay, so that is the most direct way. So I'll show you later on. So once we proceed with our examples. And once we are sure, okay, that once we are already sure that our equation is homogeneous, and then we could proceed with our second step, and that is we're going to substitute. Okay, there are 2 ways on how to substitute. It's either we're going to substitute y is equals to vx or x is equals to vy. Okay, so y is equals to vx or x is equals to vy. That is 2. But which are we going to employ here? Are we going to use y is equals to vx or x is equals to vy? Actually, regardless. Okay, so regardless of the parameter or the relation that you will be substituting, it will yield to the same answer. However, one will yield to a shorter solution and the other one will yield to a longer solution. So of course, we do not want to waste our time. So we have to properly select. So which are we going to substitute? Is it y is equals to vx or x is equals to vy? Okay, so usually we are looking the differential dx or dy. Okay, so we are always looking at the differential dx or dy in order for us to detect, so which are we going to use? Is it y or x? So when dx is multiplied, okay, to a smaller number of terms, then we're going to use x. If dy is multiplied to a lesser number of terms, then we're going to use y. So what do I mean? So for example, if I would have x dx and then plus x squared plus y squared, so let's say this is x squared as well, and then dy is equals to 0. So which am I going to use? So I am referring a while ago that we have to take a look at the differential. So the differential dx here is multiplied to a single term, which is 1. However, our differential y here, okay, is multiplied to two terms, which is the x squared plus the y squared. Okay, so the more terms that is multiplied to the differential, therefore, the more complicated our equation will be. So in this case, although it is okay to use y is equals to vx, but that is not advisable. The advisable here is on this given differential equation, so we will be using x is equals to vy. So since it will yield, okay, a solution which is shorter as compared if we are going to use y is equals to vx. Okay, so remember the differential. Okay, so look at the differential. The lesser the number of terms multiplied to the differential, that is the advisable relation that we could substitute. Okay, so to yield a shorter solution. Okay, pero regardless, whatever you are going to use, okay, regardless whatever relation that you are going to substitute on the given differential equation, it will always yield to the same answer. But if we do not want to complicate things, okay, so we just have to properly select whether we're going to select x or we're going to select y. And once we substitute, it just so happened that homogeneous equation, okay, so homogeneous equation will always be transformed into a separable equation. Okay, so once you substituted that, and then you're going to have some algebraic manipulation, and as I have mentioned, usually the degree of the homogeneity will be cancelled out. And once that variable with the degree of the homogeneity was cancelled out, it will be transformed into a separable equation. Okay, so to better understand that, of course, we have to take a look at a particular example. And let me have that one. So let's proceed with our first example. So find the general solution of the given differential equation. So given that we have 3 times 3x squared plus y squared dx minus 2xy dy. Okay, so as I've mentioned, there are two ways on how to detect so whether this is homogeneous or not. But if I am going to, let's say, I'm going to use the original method that we've used in such a way that we're going to substitute x into lambda x and then y is equals to lambda y, and that will give us 3 times 3 x squared will become lambda squared x squared plus y would be lambda squared y squared dx. Then minus 2, x is lambda x, and then y is lambda y, so that would give us lambda squared x and y. dy is equals to 0. And from here, so there are 3 terms that are involved. So the first term, the second term, and the last term. And as you can see there, so lambda squared is present on all the terms. So that one could be factored out. So the lambda squared, and then that would be 3. So multiplied it with 3x squared plus y squared dx minus 2xy dy is equals to 0. And thus, it goes back on our original differential equation but multiplied with lambda squared. So therefore, the degree of homogeneity of the given differential equation is actually 2. So this is the first method. So how about the other method? So the other method is just look at the given term. Okay? So in this case, this is the first term. So look at the variable. The variable there is x squared. So the power is 2. Okay? So that is the first term. The second term is y squared. Again, the power of this is 2 as well. Okay? So the first term is 2. The second term is 2. How about the third term? So the third term here is there are 2 different variables. So one is x, the other is y. However, the power of x is 1, and then the power of y is 1 as well. So if we're going to add the 2, so 1 plus 1, that would still be 2. Okay, so from there, the total or the exponent of each given term, okay, or the degree of each given term is actually 2. So 2 here, 1 plus 1 would be 2 on the third term as well. So in that case, since all the terms, their power or their degree is equal to 2, therefore this is homogeneous, and then the degree of homogeneity is 2. Okay, so whichever is the method that you will be using in detecting the homogeneity of the differential equation, that would be fine. Okay, but if you are hurrying up in detecting, so what would be the degree of homogeneity, so it's always, okay, so it is always easier if we're just going to take a look, or we're just going to add up the power on each given term. And there, you'll be able to right away detect that that is a homogeneous differential equation. So once we are done with the homogeneity, we are sure that this is already a homogeneous equation, so we will be substituting. And as I have mentioned, there are 2 ways on how to do it. Okay, so that would be y is equals to v of x, or x is equals to v of y. And I already told you the technique, so that will yield to a shorter solution. That solution would be, look at the differential. So dx here, okay, so dx is multiplied with 2 terms. The first term is the 3x squared. The second term is the y squared. So therefore, there are 2 terms involved for dx. However, for dy, there's only a single term, and that is 2xy. So there's only one. So therefore, based from that observation, so it is advisable that we will be using, that we're going to let y is equals to vx. Okay, and then from there, so we're going to derive it. So dy then would be equal to, using power formula, so v dx plus x dv. And then we're going to rewrite our original equation and then substitute y as vx, and then change dy into v dx plus x dv. So we'll have then 3 times 3x squared plus, this is y squared, but y is equals to vx. So vx raised to 2, so that would be v squared x squared And then we'll have dx, so we'll just retain dx, then minus 2, then x, y there is vx. So vx times x is equals to vx squared. And then dy would be, okay, so vx squared, right? Then dy will be v dx plus x dv. So v dx plus x dv would be equal to 0. Okay. Once you substitute it here, the trick that I am telling you a while ago. So why do we need to determine the degree of homogeneity? Because it plays a role here. Okay? So since we substituted y is equals to vx. Okay? So and then the degree of homogeneity of this, the degree of homogeneity, okay, homogeneity of the given differential equation is equal to 2. And then we substituted y is equals to vx. So we have not chosen x. So therefore, we are expecting that we will cancel out x squared. Okay? So meaning the variable that we had not chosen, so which is x, and then the degree of homogeneity, which is 2. So we are expecting that x squared. Okay, so x squared will be taken out from the differential equation. And true enough. So in the first two terms, okay, so x squared, then this is x squared, and then we have another x squared for the last term. So x squared is common. So therefore, we could factor out x squared here. And then that will leave us to 3 times 3 plus v squared dx, then minus 2v times v dx plus x dv is equals to 0. And from there, so we could multiply everything by 1 over x squared. So doing so that would just cancel out the x squared. So leaving us the 3 times 3 plus v squared dx, and then distributing. So we'll have negative 2v, okay, so negative 2v squared dx, and then minus 2vx dv is equals to 0. And then, so actually we could combine, no? So distributing 3, so that would give us 1 or 9 dx plus 3v squared dx minus 2v squared dx minus 2vx dv is equal to 0. And then from here, so we could have 9 dx, and then 3v squared minus 2v squared would just simply be plus v squared dx minus 2vx dv is equal to 0. And from here, so we can factor out dx again, so giving us 9 plus v squared dx minus 2vx dv is equals to 0. And once we were, or since we were able to simplify already after substituting the relation y is equals to vx, so this time around, so we could proceed on our third step. And this is already, or we were able to transform the homogeneous equation into a separable equation. Because all of this is in terms of v. And then this one is v multiplied it with x. Okay, so doing the shortcut, so this would give us, or transform this one into dx over x. Okay, We're just going to multiply. If you want to see how it was done, so we could multiply 1 over x, so as to remove the x which is multiplied to 2v dv. And then similarly, so if we want to separate v from x, so we're going to divide it as well with 9 plus v squared. So giving us dx over x minus 2v over 9 plus v squared dv is equals to 0. And then from there, so we can now integrate. Okay, so since it is already separated, so doing so we could let u to be 9 plus v squared. And it happens that du then would be equal to 2v dv, so which is exactly our numerator. So this one would give us an ln x and then minus ln of 9 plus v squared. And that would be equal to c. However, we have introduced a relation v, or a relation y is equals to vx. So we have mentioned that y is equals to vx. So therefore, we have to transform it back in terms of x and y. So in this case, v then would be equal to x multiplied it with y. Okay? Or sorry, y is equals to vx. Or so y is equals to vx. Therefore, v is equals to y all over x. So we could substitute v then. So ln of x minus ln of 9 plus y squared all over x squared is equals to c. Then ln x minus ln of, so we can take the LCD as x squared. So giving us 9x squared plus y squared then is equals to c. And then since that would be a minus, okay, so we can combine ln. So ln then that would be x all over 9x squared plus y squared all over x squared. So remember that x here would have a 1 over 1 below is equals to c. And then from there, we could multiply this one, so the extremes and the means, so giving us the x times x squared. So we'll have x cubed all over 9x squared plus y squared. That would be our ln is equals to c. And then we could take the exponential on both sides, so leaving us x cubed all over 9x squared plus y squared is equals to c. And finally, so x cubed would be equal to c multiplied it with 9x squared plus y squared, and that would be our general solution for the given homogeneous differential equation. Okay, so this would be a bit longer solution. Okay, however, we still have a simpler example. So let's have the second example, and that is finding the general solution of the given differential equation. So given that we have xy dx plus x squared plus y squared. So although our first step here is to determine the homogeneity of the differential equation. So the degree of homogeneity. So I'm not going to use lambda anymore because there are only three terms involved here, the x and y, the x squared, and then the y squared, which is similar as the one that we had before. And in this case, we have the same thing. So x and y, that would be 2. 1 plus 1 is 2, x squared is 2, y squared is 2. Therefore, the degree of homogeneity of this is equal to 2. And then for our second step, and that is to determine, so which relation are we going to substitute? Is it y is equals to vx or x equals to vy? And as you can see here, so dx is only multiplied to a single term, which is x and y, while the dy is multiplied with two terms, x squared and y squared. So therefore, it is advisable that to have a shorter solution, so we will be using x is equals to vy. And then dx then would be equal to v dy plus y dv. So substituting it on our differential equation, so giving us, so x is equals to vy, so therefore vy times y would become vy squared, and dx is v dy plus y dv, and then dx is v dy plus y dv, then plus x squared will be v squared y squared, then plus our y squared will be y squared again, and then dy would just be dy is equals to 0. And then as I have mentioned, so something or some variable, okay, so would be cancelled out. So we had chosen y, so therefore the variable that will be cancelled out would be y. And then the degree of homogeneity is 2, so we are expecting that y squared will be factored out from the differential equation. And true enough, so y squared is common to everything. So we have the y squared here, then y squared there as well. So leaving us, so we could just factor that out, or we could just simply remove it. So since that is already factorable, so leaving us, so v times v dy, so we'll have v squared dy, then plus vy dv, and then we'll have plus v squared dy, okay, v squared dy plus dy is equals to 0. Okay, so v squared times dy, and then 1 times dy would just be dy. And then we have something that is common, v squared dy and v squared dy. So leaving us a v squared plus v squared. So we have 2 v squared dy, then plus dy plus vy dv is equals to 0. So we could factor out dy, so 2v squared plus 1, multiplied it with dy, plus vy dv is equals to 0. So this time around, so there's already a simplified version, or the transformed and simplified version of the homogeneous equation. So therefore, this is already a separable equation. So for our third step, so to separate it, so we're going to divide everything by, so for dy, so we're going to move out 2v squared plus 1, and then the unnecessary variable on dv, it's only y. So therefore, we'll just have dy over y, then plus v dv all over 2v squared plus 1 dv, then that would be equal to 0. So since this is already separable, so we can right away find the solution of the differential equation by letting u to be equal to 2v squared plus 1. However, the derivative of u is 4v dv. And the one on our numerator is v dv only. So therefore, we'll have a neutralizing factor which is 1/4. So giving us dy over y as ln y. And then plus our neutralizing factor 1/4. And then we'll have the ln. Okay, so since the denominator, the derivative of the denominator is the numerator, therefore that is an ln function. So an ln of 2v squared plus 1 is equals to c. And then again, our v. So what did we substitute? So x is equals to vy. So, but x is equals to vy, therefore, v is equals to x over y. So substituting, so ln y plus 1/4. So ln of, we'll have 2v squared. So we'll have 2x squared all over y squared plus 1 is equals to c. So combining again, so ln y plus 1/4 ln of y squared. So I'll have 2x squared plus y squared times 1 is y squared. Is equals to c. However, so we could multiply everything by 4. Okay. So as to remove. Okay. So as to remove the 1/4 there. Okay, so multiplying everything by 4, so giving us 4 ln y plus ln of 2x squared plus y squared all over y squared is equals to c times 4 is still c. And then applying the properties of logarithm, so 4 ln y is the same as ln y raised to the 4th plus ln of 2x squared plus y squared all over y squared is equals to c. And again, there are 2 ln, so which are added. So another property there, so we could combine. So giving us an ln of y to the 4th, multiplied it with 2x squared plus y squared all over y squared is equals to c. So y squared would cancel out, so giving us a y squared above. So ln of y squared, so multiplied it with 2x squared plus y squared is equals to c. So taking the exponential function of both sides, so yielding to a general solution of y squared, multiplied it with 2x squared plus y squared is equal to c for our final general solution. Okay, so this is almost the same as our first example, but this time around, so instead of using y as our relation in terms of vx, so we are using x in terms of vy. So let's have another variety of an example. So this time around, so we will be solving the third example. So we have the x dx plus sine squared y all over x, multiplied it with y dx minus x dy is equals to 0. So for our first step, so how many terms do we have here? So we have the first term. The second term is the y dx, multiplied it with sine squared y all over x. And then the second term would be x dy, multiplied it again with sine squared y all over x. So how do we find the degree of homogeneity? So the degree of homogeneity here is, so we have 1. So since it only involves x, so here it's 1. Okay. So for our second term, so the whole of this is our second term. So the degree of y is 1. However, we have y all over x. We have a variable, so which are on the angle of our sine function. However, the degree of the y here is 1, the degree of x here is 1 as well. And it involves a division. So what we'll be doing there is just 1 minus 1, that would be 0. So 0 plus 1, that would still be 1. So therefore, the homogeneity or the degree of the second term is 1. And the same is true with our third. The degree is still 1. So all in all, the degree of homogeneity of this given equation is 1. So second step. So we have dx. Okay. So this is dx. Then we have another dx there. So meaning our dx is actually multiplied to two terms. One is multiplied with x, the other is multiplied. Okay, so one is multiplied with x. Okay, the other one is multiplied with this. While dy is only multiplied with x and sine squared. So therefore, the easier solution here, or shorter solution rather, so would be letting y again to be equal to v of x. Then dy would be equal to v dx plus x dv. So substituting, so x multiplied it with dx, so we're just copying it. So since it is the y that we will be changing, and then we have plus sine squared, and then y is vx all over x, then multiplied it with y, so which is vx dx, then minus x, our dy is v dx plus x dv. And all in all, that would be equal to 0. And simplifying this one further, so it gives us x dx plus sine squared v. So since x will just canceled out. And then multiplied everything with vx dx minus, so distributing x is vx dx as well. Then minus x times x dv, will have x squared dv is equals to 0. And from here, so vx dx would just canceled out, and giving us the x dx, and then minus x squared, correct? So x squared sine squared v dv is equals to 0. So sine x squared sine squared v dv. And as I've mentioned, the degree of homogeneity, by the way, the degree of homogeneity is 1. And then we had not chosen x. And then the degree of homogeneity is 1. So therefore, we are expecting that x should be cancelled out on the given differential equation. And again, so from here, so x is common. And that is, we could factor out x, multiplied it with dx, minus, so x squared divided with x, it's just x, sine squared v dv. Okay, so sine squared v dv is equals to 0. So x then would cancel out, and we'll have dx minus x sine squared v dv is equals to 0. And then using separable equation, this is transformable into separable equation, so giving us the separated equation to be equivalent to dx over x, then minus sine squared v dv is equals to 0. So from here, so we can already integrate dx over x, but not sine squared v. So to determine the solution of the sine squared v, so we will be using trigo identity. So in such a way that sine squared v is actually equal to 1/2 multiplied it with 1 minus cosine squared v. And doing so, we'll have dx over x, then minus 1/2 1 minus cosine squared v dv is equal, or sorry, cosine, that's not cosine squared, that should be cosine 2v. And the same is true with this one, cosine cosine 2v. Okay, so cosine 2v. So leading us into dx over x minus, so distributing the 1/2, so we'll have 1/2 dv, then plus 1/2 cosine 2v, which equals to 0. So this time around, so we'll have dx over x is ln x, then minus 1/2 v, so for the dv, and then for cosine, the integral of cosine is sine. Okay, so cosine is sine. However, we have u, which is 2v, so therefore du would be 2 dv. So 2 dv. So from there, so we only have dv, so our neutralizing factor would be equal to 1/2. So we'll have the neutralizing factor, or we have the 1/2 there, and then we have the neutralizing factor of 1/2, then the integral of cosine would be sine 2v is equals to 0. So giving us an ln x minus 1/2 v plus 1 over 4 sine 2v. But what we've used is y. Y is equals to vx. So therefore v is equals to y all over x. So giving us an ln x minus 1/2 of y all over x plus 1/4 of sine 2y all over x is equals to c. And multiplying everything by 4, so giving us 4 ln x minus, or sorry, we could, that would be fine. So we'll have 4 over 2 will be 2 y all over x, and then plus sine 2y all over x is equals to 4. Or if we want, so we could make this one as ln x to the 4th, and then minus 2y all over x plus sine 2y over x is equal to 4. So that would be our final implicit solution, so for our given differential equation. So I just need to correct something. So this should not be 4. So since this is a general solution, so this should be equal to C. So giving us the final solution, final general solution to be ln of x to the 4th minus 2y all over x plus sine 2y all over x is equal to C. And that's it for our homogeneous equation.